Welcome to part 2 of the video on definite integrals. In this second video we're going to talk a little bit more about the intuitive idea behind the definite integral, and we're going to introduce the notation used for definite integrals. So let's review what we saw in part 1. We considered the physical problem or a physical situation. We consider a particle that is moving at a certain velocity that changes with time, and we say that we have velocity as a function of time given by this graph. So we have velocity, the function velocity, and the problem that we wanted to solve was that given this velocity we wanted to find the distance traveled by the particle during a certain interval of time. So what we did was we took a very small interval dt, is a very small interval of time dt. So, and we took it very small such that we could consider that the velocity during this interval is constant. During this very small interval there is some change in the velocity, but as the interval is so small, we can consider that there is no change and the velocity is constant. So as the velocity is constant, the distance traveled is given by this velocity, there is a constant, times the duration of this interval, there is dt. So the distance is v dt. And this also gives, in this graph, v dt is also the area of this rectangle here, that is in pink. So we solved this problem in the case of very small interval, and then we talked about how to do this when we have a larger interval, for example from 0 to a number t to 0. And what we did here, we divided this large interval into many small intervals like this, and we solved the problem in each of these intervals, and then we solved this, we summed the area of each of these rectangles. That gives the distance traveled. So the real solution is given with when you take the limit as the number of these rectangles approach infinity, and when you do that, we saw that approaches the area under the curve. That gives us the real distance traveled during this interval. So now let's try to fix our notation. We saw that the distance traveled during each small interval is ds equals v times dt, and the distance over a longer interval is the sum of the distance at a very large number of smaller intervals. So when we take the limit of this sum as the width of these intervals approaches 0, so the number of intervals approach infinity, we get the definite integral. And we use this notation that you are already used to, this symbol here, this curvy s, that it is the same symbol for indefinite integrals. And well, you use v dt. Now you get to understand why you use the dt here, because we are taking here an infinite sum, really. That is the limit of a sum as the number of terms approach infinity. And what is new here are these two numbers, 0 and t to 0, and these two numbers only conveyed in what interval you want to integrate. Let's talk a little bit about that. We're going to talk a little bit about that later. So we saw that the sum of the areas of these rectangles approach the area under the curve, and the area under the curve is given by s. So this is an approximation to s. As you take more and more rectangles, you get better approximations, and when you take the limit as the number of rectangles approach infinity, you get this pink area here, and this area is s. That is the integral, the definite integral of v dt. And I forgot to tell you that this is read definite integral from 0 to t sub 0 of VDT. And in this special case we took, well, let's talk about the notation. This is the notation for definite integral. We have the symbol that is really, the symbol is really comes from s of sum, and in this case we have kind of an infinite sum because it's the limit of a sum, and the number here below is the lower limit. We call it the lower limit, and this other number is the upper limit, and they only indicate the interval over which you are iterating. And f of x dx is the area of each small rectangle. This comes from what we saw before in this graph, that we saw that VDT, in this case v is over function f, VDT gives us the area of the rectangle. So this notation only tells us that we are taking the sum of infinite small rectangles like this, but infinitely small, and we're taking the sum, of these rectangles from t sub 0 to t sub 1, and this is what this notation means. So you don't have to get scared of this notation. It's only that it is only like notation for a sum. So in the next video we're going to see some properties of the definite integrals. So that's all for now. Thank you for watching and see you next time.